Now, I will solve problem number 1.47 for you. Let's read the problem statement. A solid body starts rotating about a stationary axis with angular acceleration. There is any body, it starts rotating. Initial angular velocity is 0. It starts rotating, means initial angular velocity is 0. Angular acceleration is a into t. Here a is 2 into 10 to the power minus 2 radians per second square, per second cube in fact. How soon after the beginning of rotation will the total acceleration vector at an arbitrary point of body forms an angle 60 degree with velocity vector? The total acceleration vector at 60 degree with velocity vector. What is that time? This is the question posted on us. Now, this is any arbitrary point at any instant. Let us say this is any arbitrary point at this instant. First of all, after some time, what would be its angular velocity or what would be its velocity? Beta, which is equal to at, is d omega by dt. This is the rate of change of angular velocity. Hence, d omega is at dt. I can integrate it. Integral of d omega is a integral of t dt. At 0 time, angular velocity is 0. At any time t, angular velocity is omega. I can always write it like this. Integral of d omega is omega. T dt is t square by 2. So, omega is equal to a t square by 2. This is angular velocity at any time. Now, velocity is omega into r. A t square by 2 into r, and this is the direction of velocity. This is the direction of velocity. It's tangential. Now, that as when the acceleration vector is at angle 60 degree with velocity vector. So, let's try to understand the acceleration vector. We'll have two acceleration here, radial acceleration and tangential acceleration. Radial acceleration is omega square r. This radial acceleration is omega is given to us a square t to the power 4 by 4 into r. This is the magnitude of radial acceleration. मैं रेडियल एक्सीलरेशन का मैग्नीट्यूड इस जगह पर ऐसे ड्रॉ कर देता हूं, रेडियली इनवर्ड. दिस इज द रेडियस वेक्टर and this is the radial acceleration of the particle shown along with its direction. Tangential acceleration is angular acceleration into radius, or tangential acceleration is at into r, and this is tangential acceleration of the particle. The direction of arrow suggests us its direction and the length of arrow suggests us its magnitude. Now, what is the net acceleration vector? In order to get the net acceleration vector, this is net acceleration vector. I will say net acceleration vector is the vector sum of radial and tangential acceleration. And they says that this net acceleration vector is at some angle phi with velocity vector. बिल्कुल साफ इस बात को बता दें, velocity vector is parallel to tangential acceleration vector. So when acceleration vector at phi with velocity, you can also say acceleration vector at phi angle with tangential acceleration vector. You can always say this. Now, they have velocity vector or they have tangential and acceleration vector at an angle phi with tangential acceleration. So I can write tan phi is equal to AR upon AT. AR is just A square T to the power 4 R by 4 whole upon AT is AT into R. Observe that R term got cancelled and the equation would reduce to A T cube by 4 or T cube is equal to 4 tan phi upon A, or the desired time. The answer to the problem is cube root of 4 tan phi upon A. Now you can substitute in order to get the answer. This T is equal to cube root of 4 into tan phi. Phi is equal to 60 degree. So 4 into root 3 upon, for A I will write 2 into 10 to the power minus 2. And this is a solution for problem number 1.47. See this, that asks that at what time acceleration vector would be at some angle with velocity vector. This is the net acceleration vector, and at angle with velocity vector means also angle with tangential acceleration. Velocity of particle is always in tangential direction. So the direction of velocity is also same as the direction of tangential acceleration. This is angular acceleration. This is the definition of angular acceleration. From here we will get the expression for angular velocity, and we can get the magnitude of tangential velocity at any time and the direction of tangential velocity at any time, radial acceleration, tangential acceleration and the net acceleration. नेट एक्सीलरेशन वेक्टर का डायरेक्शन हमने देख लिया और उसकी वेलोसिटी के साथ में फाई एंगल के लिए कंडीशन देख ली और उस कंडीशन को हमने अप्लाई कर दिया. प्लीज नोट इट डाउन. Now let me solve problem number 1.48 for you. A solid body rotates with deceleration about a stationary axis with angular deceleration. Angular deceleration is given. Angular deceleration. That angular deceleration is directly proportional to root of angular velocity, where omega is angular velocity. Find mean angular velocity. Find mean angular velocity of body averaged over the time of rotation. If at initial moment angular velocity is omega naught. Now, mean angular velocity over the total time of rotation. First of all, this angular deceleration. Angular deceleration, I will write it like this. This angular deceleration is minus or d omega by dt is equal to k root of omega. It's directly proportional to under root of angular velocity. So I put an equality sign along with the constant k, and since it's angular deceleration, I put a negative sign here. Now this k is a positive constant. Now this k is positive constant. I need to solve this differential equation. In order to solve this, I will rearrange it like this. D omega by root of omega is equal to minus k dt. And now I integrate it on both the sides. Integral of d omega by root omega is equal to minus k integral of dt. At 0 time, angular velocity is omega naught. At any time t, angular velocity is omega. Now this would give me 2 root omega from omega naught to omega is equal to minus kt from 0 to t, or root of omega minus root of omega naught is equal to kt by 2, or root of omega is equal to root of omega naught minus kt by 2. One can always write this equation after integrating. Now, it stops when omega becomes 0. It stops when omega becomes 0 or root omega becomes 0, and that time is equal to t naught. I will put this condition here and I will get t naught as equal to 2 root of omega naught by k. This is the time when this body would stop. Now, mean of angular velocity. In order to write the mean of angular velocity, I will write expression for omega, and that expression for omega would be equal to k square by 4 t square minus k root of omega naught into t plus omega naught square. I will square this side thing. This is the expression for omega as a function of time. Now, mean of angular velocity is integral of omega dt over 0 to t naught time upon integral of dt over 0 to t naught time. This is the expression for mean angular velocity. So this mean angular velocity of particle would be given by integral of k square by 4 t square minus k root omega naught t plus omega naught square dt. And this goes from 0 to t naught time, that is 2 root of omega naught by k upon dt, 2 root of omega naught by k. We need to solve this. Mean of angular velocity is k square by 4 into t cube by 3 over 0 to 2 root omega naught by k minus k root omega naught into t square by 2 over 0 to 2 root omega naught by k plus omega naught square t over 0 to 2 root omega naught by k whole upon 2 root omega naught by k. Solve it and you would get the mean of angular velocity as omega naught by 3. The k term would get cancelled. The problem simply involve the definition of mean angular velocity and angular deceleration. There is angular deceleration, the definition of angular deceleration, and solution of the simple differential equation in order to get the angular velocity expression, and to apply the condition that when the particle stops, angular velocity becomes 0, root of angular velocity should become 0, and that time is t naught. We will determine time t naught like this, and then we will apply this definition of mean angular velocity. This is the standard definition of mean of any quantity, mean of angular velocity. Simple integration, definite integration, and then solution. Please note it.